All right, so now we're going to look a little bit more into the velocity and acceleration, more specifically the acceleration, now that we understand the concept of the unit tangent and unit normal vector. So a couple things just to recall, that we talk about the velocity, okay? If we're talking about an object traveling at a constant speed, okay, velocity and acceleration vectors are going to be orthogonal to one another. And the dot product would then give us 0. Okay? But if the object's not traveling at a constant speed, then that's not necessarily going to be the case. We can't necessarily say that. And honestly, and a lot of times, objects are not traveling at a constant speed. So we're not going to see this velocity and acceleration vector being orthogonal to each other. But we are going to look at an orthogonal relationship within the acceleration vector. So if we think about how velocity and acceleration relate to the position function, the velocity tells you how the position is changing over time, and in which case we also describe that as speed in some instances when we look at either the absolute value of the velocity or the magnitude of the velocity when we talk about it in terms of vectors. So the velocity vector tells you how the position vector is changing over time. And then the acceleration tells you how the velocity is changing over time. But if we look at all these things as vectors, more specifically velocity and acceleration as vectors, vectors have two components. They have two components in that they have the magnitude and they have the direction. And if acceleration is telling you how the velocity is changing, and velocity is made up of two parts, magnitude and direction, then we need to figure out how the acceleration will tell us how each of those things is changing. How is the magnitude of the velocity vector changing? And remember, the velocity vector's magnitude is the speed. So how is the speed changing? Which is what you would typically think of as what acceleration is describing. Acceleration describes whether or not the speed is increasing or the speed is decreasing, in which case we talk about acceleration and deceleration, and oftentimes we just describe that all as acceleration. But when you often think about how is the speed changing, which again is the magnitude of the velocity vector, how is that changing? Acceleration can give us that in one component, and that component we're going to call the tangential component, okay, of the acceleration vector. And then we can also figure out how the direction of the velocity vector is changing. Okay. So if we want to look at how the direction of the velocity vector is changing, we can look at another part of the acceleration vector, in which case we're going to call it the normal component, and that's going to describe the change in the direction. But what we have to do is we have to pull the acceleration vector apart to find this tangential component and this normal component. And these are basically encoded inside the acceleration vector. But if we decompose the acceleration vector into two separate vectors, being the unit tangent and the unit normal vector, we can see how the acceleration vector will describe the changes that are occurring in the velocity vector as they relate to both magnitude and direction. And again, we're going to call it the tangential component, which we're going to use a sub t to describe that, and the normal component, and we'll use a sub n to describe that. So it's a pretty quick way of doing this. It's not a very complicated proof per se to see how the acceleration vector gets decomposed. In practice, it's a much longer process, but we'll show you how to get through that here with this example. Okay, so a few things to make this look a little bit nicer. One is we're going to use this cursive v of t to denote the magnitude of v of t, which is your speed, right? So we're going to use that notation there. And we're going to say, well, the velocity vector is this speed times the unit tangent vector. Now, where's that coming from? Well, think about it this way. We know that the position vector would give us our vector valued function, okay? And that would describe the curve. And then the derivative of that position vector would give us our velocity vector. And what we could do is if we write it as the magnitude of v of t times the unit tangent vector, it really is just saying this is r prime, because what is the magnitude of v? The magnitude of v is the magnitude of r prime of t. And the unit tangent vector is r prime of t over the magnitude of r prime of t. And so these would cancel, and you see, it's still just, v of t is still just the magnitude of, it's just r prime of t. But we're going to write it like this, and then we're going to swap this magnitude of v, which again is just speed, okay? But we're going to rewrite it using this little cursive v of t to make it look nicer. All right, so if we go with this notation for v, then in order to find the acceleration vector, we got to take the derivative of v. But this is a product right here, so we would have to use the product rule, in which case we're going to say we have v prime times t plus v times t prime. Okay, so the speed derivative of the speed, which is what this is right here, times the unit tangent vector plus the speed times the derivative of the unit tangent vector. And that's again just the product rule. Then we're going to rewrite this piece over here using this. Very similar to what we did when we started this whole thing off. I didn't change anything for this first piece, it's still this piece is right here. But here's where we're going to change it. So how do we get to this? Well, again, we're going to sort of do the same concept of what we did previously. I'm going to take this t prime and I'm going to swap it out for the magnitude of t prime times n. Okay? How? Well, if I look at t prime, I can write t prime as the magnitude of t prime times t prime over the magnitude of t prime. Because these would just, this and this would just cancel each other out and still give me t prime. But if I write it like that, this is what we call the unit normal vector. So what we really have is the magnitude of t prime times n. And I really should have put a dot there because that's dot product, so just times n. So you see how this turns into this fairly easily. And that's what we're going to put here. So then what we're going to do, if I get rid of some of this, is we're going to take this right here, and I'm going to call that this tangential component. And what is it? It's the derivative of the speed. Derivative is change. So this represents the change in the speed, which is what you would typically think of as your acceleration. This here is what we're going to call this a sub n, the normal component, and that's going to represent the change in the direction. Now, this magnitude of t prime, this component here, has something to do with what we're going to talk about in the next lesson that deals with something called curvature. And if we're trying to say that this describes the change in the direction of the velocity vector, and this has something to do with curvature. Curvature is the amount of turn a curve has, okay? And we'll get more into that next time. You're going to see how these are more closely related in the next lesson. But nonetheless, this whole component we're going to call a sub n, and this is going to describe the change in the direction of the velocity vector. So again, acceleration should describe the change in the velocity. But velocity as a vector has two components. it has its magnitude, which we call speed, and it has direction to it. So we want to figure out how does the acceleration vector describe both of those changes. And if we decompose the acceleration vector into essentially the sum of these two vectors, and that's really what this is. So if you take a close look at this, this is looking at the acceleration as the sum of two vectors, the unit tangent vector and the unit normal vector. And these coefficients in front, which we're going to call the unit tangent, unit normal vector, are going to help describe those changes a little bit better. Well, think about what happens when you add two vectors together. When you add two vectors together, you get the diagonal. So if I take a sub t, t, and I have this vector as a sub t, t, a sub t would just be some multiple of t. Remember, t is a unit vector. So a sub t would just be a multiple of that, which would just change the magnitude of t itself. And then I have a sub n, n. Well, again, same thing. N is a unit vector, so a sub n, n is just changing the magnitude of that normal vector. But remember, it's always going to be orthogonal to t. So a sub n, n should also be orthogonal to t. Well, the diagonal of that box that we just created, now let's do that better. The diagonal of that box that we just created is the sum of these two vectors, which we're saying is the acceleration vector. So we took this acceleration vector here, we broke it off into its two component pieces, and the sum of these two component pieces are what makes up the acceleration vector. In each of these components, we describe how this acceleration vector is describing how this velocity vector is changing. It might seem small, but it really is giving us this additional information that we really couldn't get just out of the acceleration vector. You know, when we look at acceleration as a function, not as a vector, but as a function back in Calc 1, it was very easy for us to describe how the acceleration, or very easy for us to see how the acceleration is describing the change in the velocity, purely as a change in speed. But when we start to think of it as a vector, it's a lot harder to get that information. So this tangential and normal components will help us do that. So then let's see an example of how this actually is done in practice, how we decompose an acceleration vector to really see the changes that are happening within the velocity. So here's an example. And it says we want to decompose the acceleration vector of this function into the tangential and normal components at this particular t value. Normally, this is not a very easy task. It's a fairly long problem, and even this one is pretty long. But it's made easier by giving you all this at a particular t value. If I asked you to just generally decompose the acceleration vector for a given vector valued function and not at a particular t value, this becomes even more difficult. We'll look at this easier one so we can get through this. So first thing we need to do is actually find the acceleration vector that we're going to decompose. So we have r of t to be this t squared 2t ln t. And we have r prime can be found, which will be our velocity. And that's going to be 2t, 2, and 1 over t. Okay. And then we could find r double prime, which would be the derivative of our velocity, which is our acceleration. Let's put some arrows here, which is our acceleration, which again is pretty easy, 2, 0, and this will be negative 1 over t squared. Okay? So there's our acceleration vector. So here's our position vector, here's our velocity vector, here's our acceleration vector. And each one describes the change in the previous. Acceleration describes the change in velocity, velocity describes the change in the position. And if we find the magnitude of the velocity, that'll tell us the speed in which the object is traveling along the position curve. But really, we want to look at acceleration in a little bit more detail. How does this vector describe what we would typically think of as acceleration? How does it describe the change in the speed? Even further, how does it describe the change in the direction of the velocity vector? So, in order to do this, we're doing it at a particular t value, so then let's look at a couple things. We'll look at r of a half, r prime at a half, and r double prime at a half. Okay, so we're looking at the position, the velocity, and the acceleration all at this particular location where t equals a half. So in the first one, we're going to get the vector, 1/4, 1, and log of a half. In this case, we're going to get 1, 2, and 2. And in the last case, for the second derivative at a half, we're going to get 2, 0, and negative, 4. Okay? So this is telling me the particular location that we're in on the curve, right? This is the one vector, but that vector points to the point with its corresponding components. This is the velocity vector at that location, okay? And this is the acceleration vector at that location. But how does that acceleration vector tell me that I'm speeding up or slowing down? And again, the change in direction. So here's the decomposition. So again, the acceleration can be written as a sub t plus a sub n. Right? That's the decomposition that we want to get to. So we need to find all 4 of these components. We need to break this vector down into these 4 pieces, and we'll be able to describe what we want to describe. So the first thing we're going to do is we're going to find t, okay? Which we know we have a formula for already. That is r prime over the magnitude of r prime. Okay. And for this particular location, if we want to find t at a half, we have r prime at a half, which is 1, 2, 2. And then we want the magnitude of that, which would be the square root of 1 plus 4 plus 4. So that's going to be the square root of 9, which is 3. So then I'm going to get 1/3, 2/3, 2/3. So there's t. Pretty easy to find at this particular location. If I just said find t generally, if we weren't doing this for t of a half, if we had to find the unit tangent vector overall, then I would take this vector in the t format, not with a value plugged in for t, and then I would have to find the magnitude of that, and you could see that this would look a lot messier in terms of how we found the unit tangent vector for just a general t, but still could be done. Okay. Then, next thing I want to do is I want to find a sub t. Now, there's a couple of ways we can find a sub t. One way we can do it is it's the derivative of the speed, right? It's the change in the speed that we saw when we did the decomposition just a few minutes ago. So I could look at the velocity vector, which is here, I could find the magnitude of that and then take the derivative of that, which you can see could be really messy, okay? Trying to do it as this, we had this like cursive v prime, okay, which is really the derivative of the speed, right? It was just basically the speed, and we did the derivative of it. It could get pretty messy. I mean, trying to find the magnitude of this thing, and I can't do it for this because if I try and find the magnitude of this and then take the derivative, it's just going to be the derivative of a constant. It's going to give me 0, regardless of what it is. So I can't do it after I plug in a half. I have to do this before I plug in a half. So that's going to be kind of messy. So we're not going to do it that way. Even though that's what it represents, there's a simpler formula to find a sub t. And there's actually a ton of formulas to find a sub t. If you look in your book, if you look online, there's going to be all kinds of formulas for a sub t. The simplest formula for a sub t is to do a dot t. And the reason why a dot t works, if I just show you real quick, is remember, a is a sub t plus a sub n. If I do that dot t, well, we saw some properties of dot product with addition, so distribution property. This will distribute in here and here. So I would have a sub t dot t plus a sub n dot t. Now remembering that n and t are orthogonal to one another, that means this dot product right here should be 0. So then that means this is a sub n times 0, so that's just gone. Also recognizing that t is a unit vector, the dot product of a vector in itself should just give you the vector's magnitude, the square of the magnitude. So in which case this should be 1 squared, which is just 1. So I should have a sub t times 1 plus 0. So, and this should be, this is not dot product. This should be a sub t times 1 plus 0, which you see is just going to give me a sub t. So you see why a dot t gives you a sub t. So it works. And it's the easiest way to find a sub t. Reason being is we know the acceleration and we just found the unit tangent vector, specifically at this location. So if I wanted to find a sub t at this specific spot at a half, I should do a at a half dot t at a half, which we have because a at a half is here, 2, 0, -4, dot t at a half, which is 1/3, 2/3, 2/3. And so what we get is dot product, so 2 times 1/3 is 2/3, plus 0 times 2/3 is 0, plus -4 times 2/3 would be what, -8/3. So we end up with -6/3, so we get -2. So a sub t at this location is -2. Now remember, what does a sub t represent? A sub t represents the change in the speed. So if this is your change in speed at this particular location of t value of a half, what does that tell you? That tells you what you traditionally think of as acceleration, and the fact that I got a negative a sub t, a negative tangential component, it tells me that I am slowing down at this location at this rate, whether it's, feet per second or whatever, the units of measurement are, how acceleration is typically measured. It's speed, it's slowing down because we found that this tangential component is negative. And it's at a rate of 2 whatever the unit of measurement is. If it was a positive value we found for a sub t, that would tell us that the object at this particular time, t of a half, is speeding up. The speed is increasing. But here we're finding out that the speed is changing and the fact that it's decreasing because we got a negative value. All right, so then we got a sub t and t, so then we just need to find a sub n, and we have the whole decomposition. All right, we have two more to go, a sub n and n. So remember, what do we have? We have that a at a half equals 2, 0, negative 4. That's what we're decomposing. We found out that a sub t at a half equals negative 2, and t at a half was 1/3, 2/3, 2/3. Okay? So, remember we have this a equals a sub t, t plus a sub n, n. So we need to figure out these two pieces still. So very simple. First off, we're going to do is we're going to move this to the other side. So we get that a sub n, n equals a minus a sub t, t. Remember, we know this and these two. So we can figure out what a sub n, n equals. Now, let's think about this a little bit more. To find a sub n, we can do a bunch of different formulas, but the simplest way to do it is this. We know that a sub n, n, this is a vector, okay? We know that this is a unit vector. N is a unit vector. So that means a sub n is just a multiple of that vector, okay? So if we take a vector that's a unit vector, so this magnitude here is 1, and we multiply it by something, doesn't matter whether it's bigger than 1 or smaller 1, let's say it's bigger than 1, what's going to happen is that's going to then stretch the magnitude of that vector out now by the amount we multiplied by. So if I take this vector v, which is a unit vector, and I multiply it by k, this new vector would be k times v. However, the magnitude of this new vector is the amount I multiplied by since I was starting at a magnitude of 1. So that being said, that if I wanted to find a sub n, it should be the magnitude of a sub n, n. And if this is equal to a sub n, n, it should be the magnitude of a minus a sub t, t. Okay? So, if I wanted to find the magnitude of a, which is 2, 0, negative 4, minus a sub t, t, so that would be times negative 2, so I'll make this a plus 2, since I'm subtracting it, times the vector 1/3, 2/3, 2/3, and then again, I'll find the magnitude of this. That would give me my a sub n. Well, I got to do all this computation in here, figure out what this vector is. So 2 distributes in here, here, and here. Then I add them. So I'm finding the magnitude of what? This will be 2 plus 2/3. So 2 is what? 6/3 plus 2/3. We're talking 8/3 here. 0 plus 4/3. So that'll be 4/3. And negative 4 plus another 4/3. So negative 4 is what? Negative 12/3. So negative 12/3 plus 4/3 would give me negative 8/3. So I got to find the magnitude of that, which would be the square root of what? 64 over 9 plus 16 over 9 plus 64 over 9. So what's that going to be? The square root of, what's over 9? 64 plus 16 plus 64, it's 128, plus 16, I'm really doing this slowly here. What do we got? 14, 4, 144, oh, that's nice, because the square root would give us 12 over 3, so 4. So there you go. That's an. Okay? A sub n. All right, now we just have the unit normal vector to find, then we're done. Well, we saw that the unit normal vector is a little difficult to find if we do it based off of the unit tangent vector only and do the derivative. But there's an easier way now. Since we have this decomposition, if I just divide this by a sub n, that means I divide this by a sub n, then n will equal a minus a sub t over a sub n. Well, I know all these things, right? I found this and this and this. And so I know that this vector here is this vector here, okay? Because I just calculated that. And then I have to divide that by what I found here, which is 4. So if I took 8/3, 4/3, and minus 8/3, and I divide that by 4, I get, what, 2/3, 1/3, and minus 2/3? And there's your unit normal vector. So then we put this all together and we get our full decomposition. Okay, so let's finish this off. So what do we know? We know that the acceleration is decomposed into a sub t plus a sub n. Okay? Most important part is that the a sub t is going to basically give us that what we know as the traditional acceleration component. It tells us how the speed is changing, okay? The rate in which the speed or the magnitude of the velocity is changing. And the a sub n is going to give us more information in terms of how the direction is changing. So at t equals a half, we know that the acceleration vector was, what was it? It was 2, 0, negative 4. A sub t was negative 2. T itself was 1/3, 2/3, 2/3, and a sub n was 4, and n itself was 2/3, 1/3, negative 2/3. Okay, and so a sub t being negative 2 and a sub n being 4, what this tells us is that the speed is changing at a rate of negative 2, so that would be more of what you would think of traditional decelerating, the fact that it's a negative, and the direction is changing by a rate of 4. So that gives us some information a little bit more about how the velocity is changing, right? Acceleration is the change in the velocity. But since velocity has two components to it, it has both magnitude and direction. It has both speed and direction, essentially. We want to figure out how is the speed changing here, how is the direction changing here. And what we did is we took that acceleration vector, which let's say is this acceleration vector at t equals a half, so specifically this acceleration vector, and we broke it down into these two components, okay? Where this is the a sub t piece, and this is the a sub n piece. This picture is not accurate whatsoever, but you know the acceleration is the diagonal of that box. These should always be written at a 90-degree angle. Other than that, you know, these components are really probably the most important parts. So the a sub t and the a sub n out of this whole decomposition is really what we're going for. How is the speed changing? How is the direction changing?